All right, we're going to get started here on chapter 4 now. We're going to start with extreme values of functions. So the really good use for this is this actually has a lot of practical applications for uh, making things optimized. All right, so that's what we're going to basically look at. We're going to look at applications of derivatives, particularly in optimization. And that basically means we're going to find maximums and minimums from graphs. And so the use for this is if you have a relationship you're trying to optimize, if you can graph the two things together and find the maximum or minimums, maybe you want the minimum cost or you want the maximum profit or something like that, then if you can graph them, you can use these methods to find those peaks, those highest and lowest points of your data. It can also be used to make things more efficient. A classic example, which we will cover later when we specifically look at optimizing real situations, is a Coke can. Like a can of soda, if you have 12 ounces of liquid, there's a reason that Coke cans are the dimensions that they are. If you made them taller and skinnier to still hold 12 ounces, it would actually take more aluminum than it does at the current height and thickness that they are. And again, if you made them shorter and thicker and wider, again, it would take more aluminum to make the can to hold that same 12 ounces. So we'll do that example later on. But just the idea, there's a whole lot you can do with this right here. In addition, you can actually use this to help you figure out what the graph of a function will look like. You can go through and find all these key points, these optimized points, and actually go through and do the graphing as well. And so we'll look at that just a little bit. So our goal here is to find extreme values, that's maximums or minimums, by using the derivative. So here we have a definition. Let f be a function with domain D, then f has an absolute maximum value on D at a point C if f of x is less than or equal to f of C for all x in that domain, and an absolute minimum value if on D on that domain at C if f of x is greater than or equal to f of C for all the x in that D in that domain. So what this is saying is essentially if we have some sort of function going on here, right? I'm going to zoom in on this, and we have a function that's doing something like that, and we'll say that like from here to here, this is our domain, that if we look at this lowest point, we'll call this point C, and then if we pick any other point on here, any other x value, right, that f of x will be greater than our f of C there, which is going to make that point at C here, it's going to be a minimum for us. So it doesn't matter any x we pick in there, any other x value we pick is always going to have that be the case, that it's greater than at that point. And conversely, if our graph is doing something like this, right, we're going to have a maximum point up here that would be our C value, and our f of C here would be greater than any other point we might pick, any other f of x in our domain. So any of these other points we might pick will be less than it, and therefore that C point is our maximum. All right. If we have something that is an absolute extrema, they are known as global extrema. And what I mean by that is it's not just the highest or lowest point on just a specific domain, but it's the highest or lowest point of the entire function if you've got your whole domain, if you're looking at the entire thing. And so what I mean by that is I might have something like this, like a function that is shaped like this, right? And I can look on here and see, maybe I'll bring this one down here like that or something, right? I can see that I actually have this point up here and this point here. They are the absolute highest points, assuming that this is my domain from here to here, right? That this up here would be a global maximum, and this would be a global minimum, All right. Now, some of these other points, like this point here, would be a local maximum. It means it's higher than the points that are immediately around it. This would be a local minimum, lower than all the other points immediately around it. And again, local minimum, local maximums. So you'll have a difference where you might have a global maximum or a global minimum, or local maximums or local minimums. So there's going to be a slight little difference there. One is the highest point in its area, and the other is the the overall total highest or lowest point in the whole entire domain. Okay, so let's take a look here. Here we're looking at some trigonometric examples here. Our domain we're going to look at is going to be negative pi over 2 to pi over 2, like that. And we're looking at the sine function here. The absolute maximum for the sine function, that's this one here in blue, so maybe I'll write this here in blue. The absolute maximum value is this value right up there. That's our absolute, or even on this domain, it's our global maximum. And that value is 1, and it's at x equals pi over 2. Our absolute minimum value, that's going to be this value down here. It has a value of -1, and it's occurring at x equals negative pi over 2. Right? So this is our actual minimum value. This is where it's occurring. Okay? For the cosine function, we have an absolute maximum here. The value is the 1 that's here, and it's occurring at 0. So you look at the x value for where it occurs. You look at the y value for its actual maximum value. So it's a 1, and it's occurring at x equals 0. The absolute minimum values, there's actually 2 here that are the same. It occurs here at negative pi over 2 and here at pi over 2. So it has a value of 0, right? We're here at 0 at x equals negative pi over 2. And we have a value of 0 at x equals pi over 2. So we actually have 2 places there that are basically tying for the absolute minimum there. All right, next, closed intervals are special. So these aren't open ones that just go on forever and ever. If f is continuous on a closed interval, AB, then f attains both an absolute maximum value m and an absolute minimum value m in AB. That is, there are numbers x1 and x2 in AB with f of x equal to m, f of x equal to big M, and m is less than f of x. Well, m is less than, the minimum is less than all the other points in x, and the maximum is greater than all the other points in there for every other x in AB. So this is if we're on a closed interval. If we're open, like say we look at something like the graph of x squared, right? F of x equals x squared. That graph looks like this, and it goes up to infinity on both sides. We have no actual maximum there. We may have a global minimum right there, but we have no maximum value. Here we're saying if we have a closed loop, if we close the ends, we don't let it go to infinity, then we're going to have to end up with a maximum and minimum, at least one maximum minimum. I guess we could have a whole bunch of them, or all be both maximum and minimums. It's like a constant function. So basically what we need is it to be continuous. Realize my n and u's look the same there. Continuous and closed. That guarantees absolute extrema. Okay, so as long as it's continuous and closed, we are guaranteeing that we are going to get those absolute things there. So in order for it to be true, this is, I mean, I don't know why this is here. This is just restating what we just said. You know, it's got to be continuous, it's got to be closed, and it's got to be smooth and everything. So as long as that's true, then we're going to have that. So let's look at an example. Even a single point of discontinuity on a closed interval can keep a function from having a maximum or minimum. All right, so we can't have it be discontinuous at all. So let's look at this. Here we've got y equals x from 0 greater than or equal to 0 to less than 1, but it equals 1 at x equals 1. Basically what this means is we have no absolute maximum here, no global maximum, okay? Because as we approach this point, however close we get to 1, however close we get, there's always going to be a number slightly bigger than it. But if we go look at 1, then we don't have a value. The value drops back down to there. So you can't tell me what's the greatest value here. 0.9, sure, but then 0.99 and 0.999, 0.9999999. You can keep doing that forever. So you're never going to get an actual absolute maximum. So just that one discontinuity breaks it. We do have smallest values though. We don't have a largest value, but we do have smallest values here and here, okay? And so the function is continuous at every point of 0, 1, except at x equals 1, which is what breaks us from having a largest value. Next example, an extreme value need not exist on an infinite interval. So that's what I was just talking about before. This goes up forever. So we have no maximum, right? And then as far as the minimum goes here, we're going closer and closer to 0, but we're never getting there. So we don't have a absolute maximum or an absolute minimum, global maximum, global minimum. It goes to infinity. There's no closed interval, right? So it does not have a maximum minimum on the interval negative infinity to positive infinity. If we were to shut it off, if we were to say like we're only going from here to here, well then this would be our minimum and this would be a maximum, but that's just not the case here when we're going from negative infinity to positive infinity. Okay, so let's take a look at some of the local extrema that I was talking about here. So they're local extrema, and they're sometimes also known as relative extrema. Okay, so here definition, a function f has a local maximum value at a point C within its domain D if f of x is less than or equal to f of C for all x in the element of D lying in some open interval containing C. So we're looking at some like kind of just some interval around it, not so we're looking like almost like a subdomain. We have the whole domain, but we're going down to a smaller interval inside that domain and seeing if it's greater than all the points in that little subdomain. And if it is, it's a local maximum. And then the same thing for a local minimum. We're going down to some subdomain here, so we're coming in here, like say we're looking at this point here, we're coming in and we're saying, all right, we're gonna just kind of look between here and here, and if we do that, between this point and this point, somewhere in here, again, there's no real restriction on how big or small you have to make this. It could just be a point to the left and a point to the right if it needed to be. You're gonna find that you have a maximum there. And then you could do the same thing for the local minimum. Just make some little boundary on either side, however big or small you need to show that it is there. Okay? All right, so let's take a look here. Let's find those extrema. Let's look at here. So at which x value does the function have an extrema? So let's look at global. Well, when do we have a global maximum on this first graph here? Well, that's going to be right there. That's going to be our global max. And so I will leave that as red, and the maximum occurs, this is both a global max and technically a local max, and this is at x equals b, just like that. A local minimum is going to be right here, so this will be our max, our global max, and this will be our global minimum right there, and that occurs at x equals a. Okay, next we can look at local maximums and minimums. Actually, I'm sorry, I just wrote that wrong. That's not the global minimum. This is the global minimum over here. That's lower. Sorry about that. See, this is lower. So that occurs at C2. I wrote the total wrong thing there. Should have looked at the graph a little more carefully. So that's our global minimum. It's also a local minimum, if you think about it, because you can make some little arbitrary, like little sub-interval there that it is the lowest point of. And then we have local minimum here. This will be a local minimum. And we have a local max here, right? It's not the highest point because it's below this point up here, but it is locally. If I look to either side, if I'm standing here, no matter which way I walk, I'm going to walk downhill. All right, and then the same thing here. If I'm standing here, I can only walk one way. I can't walk left, so we discount that. But if I had, like right here or something, either way I try to walk, I'm going to have to step up. So that makes that that also makes it not just a global minimum, but a local minimum. And here, I can only step one way, and no matter what, I'm stepping uphill. So it's a local minimum. So the local maximums, I guess we can say at x equals C1 and x equals B. And then I can also do over here, we can do local minimum at x equals A and x equals C2. So those globals are both local and globals. For the next one, if we come look at this, global maximum, we don't have it. Right here, we can just keep approaching that point. It's discontinuous there, it's open, so we don't have one. There's none there, okay? None. And then the same thing for a minimum. This would have been our lowest point because we're going downhill coming either way, but we can't actually stand there. There's a hole there. We'd fall right through. So there's no global minimum, all right? A local maximum does occur at C, all right? If I'm standing right here and I try to go either way, I'm dropping off this and going down. So there is actually a local maximum at x equals C, and then there's no local minimum. This would have been our only candidate, but it's a hole, so there's none. You'd fall right through, okay? Can't have maximum or minimums at holes in your graphs. So now let's bring in the calculus for this. Here's our theorem 2, the first derivative theorem for local extreme values. If f has a local maximum or minimum value at an interior point C of its domain, and if f prime is defined at C, then the derivative, the valued at point C, is going to equal 0. All right, if you think about this, every time it's a local maximum or minimum, you're going to have this horizontal thing. So no matter what I do, if I pick 2 points and I tell you to draw me a line between them, that on this line starts going up, you have to start going up. There's no way, I can't get over to this point over here. I can't do it without, no matter what I try, without at some point having a tangent line that's going to be 0, like that, okay, no matter what I try. And if I do something a little different, I start off going down, then no matter what I do, no matter how long I wait, at some point, I'm going to have a tangent line also that has a slope equal to 0, assuming it's a smooth continuous graph. I don't pick my pen up or anything like that. If I could, or have any sharp corners, because I could do something like this, with a sharp corner where I never have that, but we're looking at smooth and continuous here. Okay, and if that's the case, then at that, and you notice at both those points, where I have that horizontal, right, where I have that horizontal slope is actually the highest or lowest point I get to, at least in that local area. And so that gives me that right there. So if we can find a place where the derivative is 0, then we're going to know that we've got a local maximum. And if you look at this, you can see on this left-hand side, I have a bunch of positive slopes. Positive slope, positive slope, positive slope, but the slopes are decreasing. This is a more positive slope than this, and then this is even less slope, and then we get to this point where we reach this 0 slope. And then if we move to the right-hand side, we start going from 0 slope right here to negative slopes. You see that? We made that switch to negative slopes that are getting more and more negative. as we go with that, okay? So we don't have positive slopes on that side, and the other side we have negative slopes. So pay attention to when the sign of the slope changes. That's going to also be very important, okay? And so now with the calculus, if you take a look at this, you can see all the local and maximum and minimum points that are given here. Recall that if a function's derivative at c is equal to 0, then the slope of the tangent, let me not do that in green, slope of the tangent line at c is 0. You can see that in the figure above, like right here and here, okay? You can see that there. The only places where a function f can possibly have an extreme value, local or global, are the following. Ready? All right, you can only have these at interior points. So an interior point where, so this is not on the edges, so not here, not here. Interior points where f prime of x at that point is equal to 0, okay? So basically when x equals c, all right? And that's going to occur at x equals c or x equals e in the picture above. That's c and e. Those are some of our local or global minimums. The next would be an interior point where f prime of x is undefined. Okay, that can happen there. That occurs at x equals d right there. X equals d. We don't have a slope at this point up here. We have a corner right there. So we cannot do a slope there. We can't do a tangent line there. It's not smooth and continuous. And then the last point, the last place is at the end points, not the interior points. That's at x equals a right there, or x equals b right there, the ends. Okay? All right? So this is critical. We're going to talk about critical points. An interior point of the domain of a function f where f prime is 0 or undefined is a critical point. Please note that I said that all maximum minimums have a slope of 0. I did not state that having a slope of 0 means that it is a local or global maximum or minimum. So take a look at this example here. It is possible for a point in the domain to be a critical point without having a local extreme value there, all right? Without having a local extreme value there. So look at the point, or look at the graph x cubed right here. This point right here, if you do the slope there, all right, it's going to be 0. There is a tangent line just like that goes straight across. It is 0. Maybe I'll do that in green. The tangent line there is 0, but that is not a maximum or minimum. All right, it is not one. And if you did that, you'd see that dy dx equals 3x squared. And if we evaluate that, right, f prime of 0, if we evaluate it at 0, we're going to get 3 times 0 squared, which is just 0. So we have a slope of 0 right there, but it's not. If we look over at this other one, here we have an infinite slope, right? And that's not going to give us, it's not going to give us a maximum or minimum. And what these points are called is they are called inflection points. So how in the world do you tell the difference between whether or not your slope of 0 was an inflection point or whether or not it was just a regular inflection point, or whether or not it was a maximum minimum? So if you look back here, notice that on this side of the maximum, this is our maximum, we had positive slopes, we hit the 0 slope, and then our slopes went to being negative, all right? So we had a change in sign on the slopes. Here we have positive slopes, so positive slopes. Here we have negative slopes. All right, so the sign of the slope changed as we crossed that local maximum value. And it also would change if we crossed a local minimum value. Like if this picture here, this was our minimum, negative slopes here, positive slopes on the other side. But look at the inflection point. If we look at this inflection point, look, positive slope, positive slope, positive slope, goes to 0 there at the green line, and then look, immediately returns back to being positive slopes. And the same thing over here. We've got, let me get a different color here, we've got positive slope, positive slope, positive slope, goes to 0 at that red one, and then goes back positive, positive, positive. So we don't have a sign change in our slopes as we cross that critical point. That's what makes it an inflection point. All right, so you got to kind of pay attention to the difference there. Here, our function is increasing with positive slopes, and after the point, it's still increasing with positive slopes. That makes it an inflection point. If you go back to this one, here, because our slopes are positive, we have an increasing function, and after we have a decreasing function. That's what makes it a maximum point there. All right. So, continuing on here, stuff happens at critical points. How to find the absolute extrema of a continuous function f on a finite closed interval. So you evaluate f at all critical points and endpoints, you find all their values, and you take the largest and smallest of these values. That's pretty much it. So let's take a look here. Find the absolute maximum and minimum values of f of x equals x squared on the interval x on the interval -2 to 1. Okay, so let's do this. And I think this will be the last one I do, like example here for this video, because it's getting kind of long. I might do the next one, but the last I'm going to leave for you to try, and I'll put them in the notes for you. So let's take a look here. So f prime of x, so f prime of x is going to equal 2x. That's the derivative of x squared. We're going to have a critical point. That's going to be at 2x equals 0, and therefore at x equals 0. So the critical points are x equals 0, right there. The function has an absolute maximum of 4. So now we have to actually evaluate at the boundaries. One of the tricks we can do here is actually look at the second derivative of x. That's just 2. And you'll notice it's positive. When you have a positive second derivative, so if we did f double prime of 0, it's still going to be equal to 2. It's positive. That tells us that that critical point is a minimum. All right, and we'll talk more about that later. But essentially, this function looks like this, and we have negative slope, we have decreasing negative slopes, we have our critical point, and then increasing positive slope. What the second derivative does is it tells us how is the slope changing. And you'll notice the slope here. If we look at the slope of the tangent here, it's like that. If we look at the slope of the tangent here, it's like that. At our point here, it's like that. And over here, it's like that. Notice our slope. We start with a slope like this, then we get a slope like this, then a slope like this, then a slope like this. And this is actually rotating as we move around. That slope is rotating counterclockwise. And counterclockwise is considered a positive rotation. Positive second derivative across that point makes it a minimum because that's the direction the slopes are changing. They're going from negative slopes to positive slopes, makes it a minimum. So just a little extra something there to help you notice this. So now we also have to look at the boundaries. For the boundaries, we have to look over at -2. So f of -2 is going to equal -2 squared, which is 4. And f, then we look at the other boundary at this 1 right here. F of 1 is 1 squared, which is 1. And then we have to look at the critical point. Our critical point is f of 0, which is 0 squared is 0. And so if we look at these points, we just have to pick out the greatest and the smallest of these, and we know our global maximum minimums. This is the greatest value, global max. This is the smallest value, global minimum. So it's just that easy. You look at all your critical points, and you look at your endpoints to make your decision there. So we have an absolute minimum here. If we come and graph this real quick, goes from -2 like that, 1, 2, 3, 4. So we have the point 2, 4. We go down to a point 0, and then we have the point 1, 1 right there. So our graph looks like this, right? That's our x squared graph. We have a maximum right there, you can see, which we found right there. And so we have an absolute maximum of value of 4 at x equals -2. And then we have a minimum value here right there. That's, oops, not that one. That's this one. And it's an absolute minimum value of 0 occurring at 0. Okay? So just that simple. All right. After that, I think I'm going to leave these other ones for you to try. Check out those critical points. Check out the points where the critical points where the derivative is 0 at those points, and then check out the boundary points and compare them together. In fact, I think this one might be a little more interesting if we were, you can try this one, but you should also, and I think the one I'll do for you in the notes, I'm going to change this to f of x equals -x squared plus 3x plus 9. I think that might let you see some stuff a little better. So this is the one I'm going to do when I do it in the notes, but you can try the -x squared plus 9 one without the 3x in there if you want. But I'm going to do this one for you in the notes. That's what you'll see. After that are some other ones. Try them as well. You know, try this one. You have a graph there. You can see it. Try and find them. And again, I'll put them in the notes for you to have a look at. Okay? I think that is pretty much everything for this one. And that's just, I think, going to be it. All right. Thank you.